So tonight we'll just do part A of this two-part PowerPoint, and this is all about where chemistry comes alive. To try to make it sound interesting for you, it's just chemistry. I'll let you guys read through or watch the career connection video on your own. To watch that, you'll have to download the PowerPoint onto your computer to watch it. Because again, what we're doing in here is a slightly modified version because you guys have access to online resources. I'm going to try to focus on the major topics in this PowerPoint and skip over some of the smaller ones. So our bodies are made up of chemicals, and all of these chemicals, your body undergoes chemical reactions all the time, and they are involved in the movement, digestion, pumping of the heart and nervous system. And we can break chemistry down into basic chemistry and biochemistry. Basic chemistry describes like the basis for all chemical reactions, and biochemistry relates it to biology or living things. Matter, you should know this definition. I say that because I try to write your test questions right after I lecture on the chapter, so I know exactly what I would ask you guys on. So I actually made the test questions for this chapter already, so I'm going to try to point out and highlight anything you should know, but you should know the definition of matter, which is anything that has mass and occupies space. Matter can be seen, it can be smelled, it can be felt, and weight is the mass plus the effects of gravity. So your weight will change depending on what planet you're on because of the different effects of gravity. States of matter can be a solid, a liquid, or a gas. Hopefully that's a review. A solid has a definite shape, liquid has a changeable shape, and gas has both a changeable shape and volume. Energy is the capacity to do work or to put matter into motion. Energy does not have mass, it doesn't take up space, but the greater the work done, the more energy it will use up. And this is a great animation talking about potential and kinetic energy that I'll let you guys watch on your own. Kinetic versus potential energy. Kinetic is all energy in action or in motion. So kinetic energy will be all the molecules in matter kind of bouncing off each other. Potential energy is stored or inactive energy. Potential energy can be in my water bottle because it's sitting on my desk. It has potential energy because it's higher above the earth. So when it falls, that'll turn into kinetic energy. Potential energy can also be stored in chemical bonds, and that's where we'll see a lot of potential energy in the body. It'll be stored in bonds that are binding to chemicals together. And this energy can be transferred from potential to kinetic energy if my water bottle falls to the floor. If a bond is broken in ATP, for example, energy will be released when a bond is broken, resulting in an action. Forms of energy, you should know these forms of energy. Chemical energy is stored in bonds. Electrical energy results from movement of charged ions or particles. Mechanical energy is directly involved in moving matter. And radiant or electromagnetic energy is energy that travels in waves, whether that's heat, visible light, UV light, or X-rays. Energy form conversion, it can be converted from one form to another, such as turning on a lamp, which converts your electrical current flowing into the socket into light energy. Energy conversion is often inefficient. So if energy is formed from one type of energy to another, we usually lose energy, and we often lose that energy as heat. All matter is composed of elements, and elements are substances that cannot be broken down into any simpler substance by ordinary chemical methods. So when we talk about the periodic table of elements, the elements are all of the substances on that periodic table that cannot be broken down into anything simpler. There's 4 elements that make up about 96% of the human body, and they'll be carbon, oxygen, hydrogen, and nitrogen. So a lot of the molecules that we'll talk about are made up of carbon and oxygen and hydrogen and nitrogen. So that makes up about 96% of our body, which is kind of fun to think about. I was a chemistry major. If you guys probably remember that if you had me from anatomy. So you're probably thinking, oh no, this is going to get really boring. But I think it's interesting. It's like a whole nother language too. 9 elements make up about 4% of the body, and 11 elements make up less than 0.01%. So really, our bodies are made of carbon, oxygen, hydrogen, and nitrogen. All elements are made of atoms, which are unique building blocks specific for each element that it's a part of. And the smallest particles of an element with properties of that element is an atom. And what gives each element its particular physical and chemical properties is because of the atoms that make it up. The atomic symbol, so we'll eventually show you a picture of the periodic table, and every element has an atomic symbol or an abbreviation for it. It's usually 1 or 2 letters. An example is O for oxygen and C for carbon. Some symbols come from Latin names. Na comes from the Latin name for sodium, and K comes from the Latin name for potassium. You should be very familiar with sodium potassium when we talk about the sodium potassium pump when we get to your nervous system. So you should know what O stands for, C stands for sodium and potassium. Nitrogen is a big one. So these are the atomic symbols, and then the approximate percentage of the body mass. So we talked about the 4 major elements of the body that make up 96% of us. And of those, these are what make up your body's mass. So oxygen makes up about 65% of us. Our mass, 18.5% is carbon. These are more common elements composing the human body and just the percentage that they're available. This also will tell you the function. If we go back to oxygen, it's a gas. It's needed for the production of cellular energy. So oxygen is extremely important to make cellular energy. So that's why that'll make up the majority of our body, because oxygen is literally in every mitochondria of every cell in our body. Carbon is important part of carbohydrates, lipids, and proteins and nucleic acids. And we'll see that when we see their chemical formulas. And we'll see how many carbons are in a carbohydrate, how many oxygens are in a carbohydrate, and so on. With hydrogen, nitrogen is important to make nucleic acids, which is like your DNA, genetic material. And here you can see other common body elements, and there's sodium, potassium. So I'll let you guys read through those on your own. You don't need to know necessarily the function of each element for the first lecture exam. Here is the least common, I guess you could say, chromium, cobalt, copper. These are some of the lesser common elements. And they're called trace elements because they exist in very minute amounts. Okay, so then we get to structure of atoms, which is kind of like basic chemistry. Atoms are composed of 3 subatomic particles, and you should know this. Protons carry a positive charge, so protons positive. They weigh about 1 atomic mass unit, and I'll tell you what I mean by that in a minute. Neutrons have no electrical charge, so they are 0. They're completely neutral, and electrons carry a negative charge. Electrons are so tiny that they have virtually no weight. So when we calculate out the atomic mass of an element, we don't add the electrons into that because they are so lightweight, we don't even add them in there. When we calculate out the atomic mass, we count up the number of protons and the number of neutrons the element has. The number of positive protons will be balanced by the number of negative neutrons. So all atoms in their normal state are electrically neutral. Protons and neutrons will be found in the nucleus of an atom, and electrons orbit around the nucleus, a lot like planets orbit around the sun. So chemists have devised models of how these subatomic particles are put together, and they call it, rightly so, the planetary model and the orbital model, because electrons circle or go in fixed circular paths around the nucleus. So these 2 models just explain how the electrons will spend time in paths around the nucleus, in fixed circular paths, but also in orbitals, meaning there will be a few electrons in one orbital, more electrons in another orbital further away. And I'll show you, good, we're finally getting to a picture here. So this explains the orbital model, which represents electrons as a cloud of negative charge, filling the nucleus. And a more simplified planetary model shows the electrons as two small spheres on a circle around the nucleus. You don't really need to know the difference between these two models. You just need to know that electrons circle the nucleus, and within the nucleus are the protons and neutrons. Can you guys hear me okay? Our gardener just showed up. And it's loud in my ear, but I don't know if it's loud in your ear.
You're fine. We hear you good.
Good, thanks guys. Okay. Just let me know if it gets bad. Okay, so then how we identify elements, different elements contain different numbers of subatomic particles. And they're always named for the number of protons they have. So hydrogen is number 1, and it will have 1 proton and 1 electron. Because the protons and electrons balance each other out, it's neutral. Helium is 2. It has 2 protons and 2 electrons. Lithium has 3 protons and 3 electrons, and identifying facts about an element include its atomic number, its mass number, isotopes, and atomic weight. And I'll go over what I mean by that. I promise it won't be as scary as it seems. So the smallest element is hydrogen, and it's number 1 on the periodic table. And the atomic number of an element always tells you the number of protons of that element. So here is hydrogen. It's atomic number 1. So it will have 1 proton. It has 1 electrons circulating in the orbital cloud. So it makes this element completely neutral because the positive and negative balance each other out. It doesn't have any neutrons in it, and you can see that number here. Helium has 2 protons, so its atomic number is 2, and it has 2 electrons because that will even itself out, and it has 2 neutrons. I'll tell you how we can figure out how many neutrons an element has as well in a minute. Lithium is the atomic number 3, so it has 3 protons, those are in red. It has 4 neutrons, and it has 3 electrons. So the atomic number is always equal to the number of protons within the nucleus, and it's often written as a subscript. That's a little number to the bottom of to the left of the atomic symbol. So here's lithium, and lithium has a little 3 next to it. So the 3 is the atomic number. So how many protons does lithium have?
3, right?
Just 3.
Yeah.
How many electrons does lithium have? Oops, sorry guys. Oh my, sorry. So
4.
the electrons will always equal the number of protons in a completely neutral atom. Because electrons are negative and protons are positive, electrons and neutrons will always be equal in a neutral atom. So lithium has 3 protons and 3 electrons. Easy peasy so far. The mass number of an element gives you the total number of protons and neutrons in the nucleus. And this is just simply the total mass of the atom. Remember when I said electrons don't have mass, so we don't count them. So the mass number just takes into account the number of protons and neutrons in the nucleus, and it's written as a superscript to the left of the atomic symbol. If you ever get confused of the numbers to the left of the atomic symbol, usually the smaller of the 2 numbers is the atomic number, and the bigger one on the top is the mass number. So if 7 is the mass number of lithium, and you know that the mass number is the number of protons and neutrons, and we know that the number of protons is 3 because that was the atomic number, how many neutrons does lithium have?
4.
Yes, does that make sense to everybody? So the mass number is the number of protons and neutrons, and the atomic number gives us the number of protons. So we just do 7 minus 3 equals 4, which is your number of neutrons.
So basically, you would subtract the top number from the
From the
bottom number.
number.
To get the number of neutrons. Yep. So the top number gives you protons and neutrons. The bottom number is the bottom of protons. So if you subtract them, you'll get the number of neutrons. And then how do you know how many electrons you always have?
They always equal the amount of protons.
The number of electrons will always equal the amount of protons because electrons are always negative, protons are always positive, and a completely neutral atom, they have to be neutral. So you have to have the same number of positive charges as the same number of negative charges.
Wait, I'm sorry. How would you know if it's neutral or not?
Every atom in its natural state is just neutral.
Okay.
If it's not neutral, it'll have a plus or a minus next to it as a superscript on the right side. So
Okay.
if it's not neutral, it'll have a plus or a minus.
Okay.
And those are called ions. We'll get to that. Isotopes are structural variations of the same element. Isotopes contain the same number of protons, but they'll differ in the number of neutrons they contain. So the atomic numbers will be the same, but their mass numbers will be different. So this is true in carbon. There's carbon 12, there's carbon 14, and that's referring to the particular isotope of carbon that just has different number of neutrons. So they'll differ in their mass number because they might have more neutrons or less neutrons, and neutrons are involved with the mass of an element. If that makes sense. The average of mass numbers of all isotope forms forms the atom itself. So usually the mass that we see in the periodic table is kind of an average of all isotope forms. So an isotope is just an atom with different numbers of neutrons that they might contain. So isotopes would still be a neutral element. It would just have different numbers of neutrons. And isotopes of hydrogen are shown here. So you can see the atomic symbol is the same, H, H, H. So we're dealing with hydrogen. But you can see in the superscript to the left, here's a 1, here's a 2, and here's a 3. Well, normal hydrogen with a 1 next to it has an atomic mass of 1. So we know there's just a proton in there, so there's no neutrons. Deuterium is an isotope of hydrogen, so it would be written out with a hydrogen and then a 2 for its atomic mass. So we know an isotope just differs in the number of neutrons. So we would just add in an extra neutron because we're going from 1 to 2. To go have an atomic mass of 3, hydrogen with a superscript of 3 for its atomic mass, we would add in 2 neutrons to get that isotope. All I want you to know is that an isotope is just an element with different numbers of neutrons. You don't have to know anything else, anything more than that. It's important a little bit to understand what an isotope is because we can talk about radioisotopes, which are isotopes that decompose to more stable forms, where atoms will lose some of their subatomic particles. And as the isotope decays, these subatomic particles that are being given off will release a little energy, and this energy is referred to as radioactivity. And this radioactivity can be detected and measured with different scanners. Radioisotopes are a valuable tool for our types of research in medicine. They can share some of their same chemistry as their stable isotopes, so they'll be still taken up by the body, but then they can be used in the diagnosis of disease. If you inject a radioisotope, sometimes it's easier to then see it in an X-ray or some type of imaging. All radioactivity can damage living tissue, so we use radioactivity to destroy localized cancers. Some types can cause cancer. Radon from uranium decay can cause lung cancer, but we also use some radioactive isotopes for cancer treatments. And you might have heard people undergoing cancer are undergoing radioactivity or radiation. Combining matter then. So this is where we get to molecules and compounds, and we'll eventually get into the molecules that make up your body. And I'll try not to, I know we got to get through this, so I won't dwell too much on this. Most atoms can chemically combine with other atoms to form molecules and compounds. And a molecule is just a term for two or more atoms bonded together. And then a compound is a specific molecule that has two or more different kinds of atoms bonded together. So for example, C6H12O6, this is glucose. And a glucose molecule has 6 carbons in it, 12 hydrogens, and 6 oxygens. And that makes up one glucose. Molecules with only one type of atom, like H2 or O2, which is oxygen, they're just called molecules by themselves. Most matter exists as mixtures, and you should know the 3 basic types of mixtures: solutions, colloids, and suspensions. A solution is where solute particles are very tiny. They do not settle out or scattered light. So a solution is just a mixture of solute particles in a solvent. So it makes up a solution. In a colloid, so an example of a solution is just mineral water. You know, there's stuff in that water like minerals, but you can't see them. It's completely mixed. A colloid is where you have solute particles that are larger than in a solution, and they scatter light and they don't settle out. So an example of this would be Jello. And then a suspension is where you have solute particles that are very large, they settle out, and they might scatter light. And this is where we would mix up like a sample of your blood to get plasma and settled red blood cells at the bottom. So this describes solutions, which are made up of a solvent that does a dissolving of a solute, and it would be a completely homogeneous mixture or homogeneous. That just means everything is evenly distributed. A solution's examples, they're usually transparent, like air, a salt solution, sugar. Concentration of true solutions. I don't ask you too much about mixtures and concentration, so I'm going to go over this part. Molarity is the number of moles of solute per liter of solvent. I'm going to kind of go over some of this because I don't think I asked you any questions about this. This gets into a lot of chemistry, but it has to do with the concentration of a mixture based on its molecular weight. Colloids are also known as emulsions. These are heterogeneous. And that example was Jello, and a suspension would be when blood is spun out, or a blood mixture, because when you take a blood sample and put it, when you spin it out, you'll get blood cells that'll settle at the bottom. Differences: unlike compounds, mixtures do not involve chemical bonding. Mixtures can be separated by physical means. And then let's get to chemical bonds, which is a little more of the chemistry. Chemical bonds are energy relationships between electrons of reacting atoms. Chemical bonds are not actual physical structures. Electrons are the subatomic particles that are involved in all chemical reactions. So when we talk about a bond forming between two atoms or molecules, they're really just sharing electrons. So electrons occupy an orbit or around the nucleus. Yes, thanks, Erin. I tried to get the person, but okay. Electrons occupy areas around the nucleus called electron shells. So I don't want to get here. I just want to show you a picture of this because I'm not going to ask you that many questions about it. You can go back and read those slides, but I just want to describe it to you in terms of a picture. Electrons occupy shells or orbit shells around the nucleus. And the outermost energy shell is called the valence shell, and it's complete when there's 8 electrons in it. So elements will want to share electrons between their outermost shell to try to get a complete shell to be happy. So this idea of orbits with electrons just describes electrons circle a nucleus, much like Earth circles the sun, but there'll be different orbits to them. There'll be 2 electrons in the first kind of shell or orbit, there'll be 8 electrons in the second orbital shell, and they'll just work their way out as they move further from the nucleus. And elements will want to react or bond with other elements to try to fill their valence or outermost shell. And when we talk about a molecule like glucose, C6H12O6, I think, did I say that right? When we talk about the number of atoms in a glucose molecule, they're all bounded together because they're sharing electrons between those atoms. See, isn't chemistry cool? Am I just the only one who thinks that? So simply put, when we put sodium chloride together, they're sharing electrons, they're bound together. So this is a look at chemically reactive elements. So these are some of them found in the body. Hydrogen, carbon has 4 electrons in its outermost shell. Every atom will only have up to 2 electrons in the orbital shell closest to the nucleus, and up to 8 electrons in the second outermost shell. So each shell can only hold a certain amount of electrons. So here's oxygen. Oxygen carbon has an atomic number of 6. So it will have 6 protons and 6 electrons. You can see there's 4 in the outermost shell and 2 in the innermost shell. Again, this is probably too much information. You guys don't need to know all about these shells. I just wanted to describe how a carbon will bond to a hydrogen or oxygen. They bond when they're held together because their electrons fill up each other's orbital shells, and that keeps them bound together. And that's how a carbon and an oxygen kind of join up. There's 3 major types of chemical bonds, and you should know these 3 types of chemical bonds: an ionic bond, a covalent bond, and a hydrogen bond. The ionic bond are when an ion, which are atoms that have gained or lost electrons, they've become charged and they're attracted to each other because they have opposite charges. The number of protons does not equal the number of electrons in ions. So an ion is a specific type of atom that either has gained an electron. So if an atom picks up another electron, do you think it will become more positive or more negative? What charge is an electron?
More negative.
More negative. So an ion, chloride, might be Cl negative. Chloride will have a negative charge to it if it picks up that extra electron. If an atom loses an electron, do you think it's become positive or negative? It'll become positive. If something loses a negative charge, it'll become more positive. So that's just what an ion is. It gains an electron or loses an electron. And an ionic bond are formed. They involve the transfer of valence shell's electrons from one to the other, resulting in different ions where one will become an anion. So we call the ion that gets a negative charge an anion, and one that gets the positive charge is called a cation, because we have a transfer of electrons from one atom to another. So one will become more positive and one will become more negative. The attraction of opposite charges will result in this ionic bond. So really simply put, ionic bond is just when you get 2 ions being attracted to each other. So here's a sodium ion. It's lost an electron, so it becomes positive. The chloride ion has gained an electron, so it becomes negative. And because you've heard it, opposites attract, well, that term originated in chemistry. They're opposite, so these 2 will attract to each other. And because of that attraction in an ionic bond, we get a tasty attribute, what do you call it, to add to our food to help it taste better. Sodium chloride is salt, all because of an ionic bond. Now you can impress your family the next time at dinner. Most ionic compounds are actually salts. When they're dry, they'll form crystals, and the biggest example is sodium chloride, which is salt. Here's a look of formation about how these bonds form together and how they actually come together. In an atomic level, you can't see this, but they're actually forming together like a tiny cube or a tiny salt crystal. Covalent bonds are formed by sharing 2 or more electrons. So again, ionic bond is formed when you get 2 ions attracted to each other because they have different oppositely charged atoms. A covalent bond is just a sharing of electrons, and covalent bonds are the strongest type of bond. 2 types of covalent bonds can be polar or non-polar covalent bonds. So this is just showing how we get a bunch of hydrogens together interacting with 1 carbon, and we form, they're all bonded together through covalent bonds because they're sharing their electrons in their outer shells. So covalent bonds are formed when atoms share electrons in their outer shells. They'll form a stable molecule at the end. How we write it is even more fun. Chemistry is its own language, written and read, and that's what you see here, the carbon in the center and 1 bond going out to each hydrogen. 1 single line means a single bond, and it usually means the sharing of 2 electrons. If we have a double line here, that would be a double bond. So this is how oxygen will combine. So you'll have 2 oxygen atoms, and the resulting molecule will be a molecule of oxygen gas, O2. 2 oxygens bound together because they're sharing their electrons in their outermost shells or orbits. So we write it OO, and we draw 2 lines because you can see that there's 2 sets of electrons here being shared to form oxygen, which is the air you breathe, which is what all cells need to function to make energy. Just going to keep going. Same thing, more examples of covalent bonds. We can have a triple bond. This is nitrogen gas, so we would have 3 lines and showing 3 sets of electrons being bound together. Covalent bonds can be nonpolar or polar. Nonpolar just means the electrons are shared equally between atoms, and this results in an electrically balanced nonpolar molecule, like carbon dioxide. In a nonpolar covalent bond, we get a linear structure at the end of it, meaning the structure won't have a positive or a negative side to it because everything is shared completely neutral and everyone's happy. Carbon dioxide is an example of this. CO2. So which one is this, the gray one? Is this the carbon or is this the oxygen that my cursor is over?
Carbon.
Carbon, and then the 2 oxygens are on the other side because there's 2 oxygens and a carbon in the middle. With how its valence electrons combine, we get a double bond. And if you want to learn more about that, you can take more chemistry too. A polar covalent bond is sharing of electrons, but it's unequal sharing. Because it's unequal sharing of electrons, one side of the molecule will be more negative because it has more electrons, and one side of the molecule will be more positive because it's giving up more of its electrons. So we just call this a polar covalent bond where one side is more negative and one side is more positive. H2O is an example of a polar covalent bond, and I'm just going to go right to the picture. This little delta is a Greek symbol that we often use to describe a polarity in its charge. So this is just showing how one end of water is slightly more negative and one end of water is more positive where the hydrogens are. What this means is that these hydrogens are probably giving up their electrons more to the oxygen, and oxygen's holding on to the electrons more tightly. They're still bound together with a covalent bond. They're sharing electrons, but hydrogens have more of a positive charge on their end. Because one end gets to be more positive, we get a molecule that isn't completely linear. It has a little crink to it or a bend in it. And that bend gives water some of its special properties because it bends that way. All right, so this just is a nice review chart of those types of bonds. Hydrogen bond is the 3rd type of bond. It's the weakest bond. Just remember that. Hydrogen bonds are the weakest bond. That they're not a true bond. They're more of a weak magnetic attraction. And their attractive force between a positive hydrogen of one molecule and a negative atom of another molecule. So that's why they're called hydrogen bonds, because they form just a weak attraction between a positive hydrogen of something and a negative of something else. This video shows how hydrogen bonds are formed between water. Hydrogen bonds are the weakest, and they just form between molecules of hydrogen atoms. This is a picture showing how a negative side of the oxygen in H2O gets weakly attracted to the positive side of H2O, and this dotted line represents the hydrogen bond. So they're not sharing electrons, they're just weakly attracted via the oppositely charged molecules. These water insects, this one is a water strider. It can walk on a pond really quickly because of the high surface tension of water having to do with those hydrogen bonds. Chemical reactions then. Hopefully you're all with me so far. I'll stop at 7:30 for sure, whether we get through this PowerPoint or not. Oh, we just have a couple more slides left. Okay. Chemical reactions occur when chemical bonds are formed, rearranged, or broken. And these reactions are written in symbolic forms using all the atomic element symbols called chemical equations. The reactants on one side of the equation are all the substance entering in the reaction together, and the products are all of the resulting chemical end products. And the amount of all of your reactants and all of your products are shown in a balanced equation. Compounds are represented as molecular formulas. So H2O is a molecular formula for water, describing that H2O has 2 hydrogens and 1 oxygen. Glucose is the molecular formula shown here. It has 6 carbons, 12 hydrogens, and 6 oxygen. The subscript, the number below them, indicates the number of atoms joined by bonds in that molecule. And any sort of prefix denotes the number of unjoined atoms. So if we look here, here's a reactant. So on one side of the equation, we would show H plus H, 1 hydrogen plus 1 hydrogen. What does that equal? And the equal sign in a chemical equation is always shown by an arrow, meaning it will always go in that direction. We get a product. We just put them together, they're formed, they're sharing electrons, and we get hydrogen gas. The 4 in front of the hydrogen means that we have 4 hydrogens and we're adding them to 1 carbon. So we get CH4, a molecule called methane that has a carbon and 4 hydrogens attached to it. Synthesis is any sort of combination. So taking reactions involving atoms or molecules and combining them to form something larger. So that's called a synthesis or combination reaction. And we say they're used in anabolic or building processes. So this word anabolic, we're going to come back to in physiology. You'll learn about what's an anabolic process, what's a metabolic process, but an anabolic process builds something. It synthesizes something. It'll take 2 reactants and form a larger product. These are examples of anabolic reactions taking amino acids and joining them together to form a protein. So that's a synthesis reaction. Decomposition reactions involve breaking something larger down into smaller pieces, and these involve catabolic reactions. And catabolic means you're breaking bonds to break something big into something small. And I think this is a typo here, because this should be opposite. And that's a typo in the PowerPoint. So sorry about that. Do you guys see this here? This is not right. It should be A and B react to form products of A and B separated. Sorry about that. That's a typo there. But hopefully that makes sense. Decomposition is a reverse of a synthesis reaction. So this should be flipped around. An example of this is taking a glycogen molecule and breaking it down into its individual glucose products. Glycogen, maybe you remember from anatomy, maybe not, is the storage form of glucose. And glycogen is in your liver, and it stores extra glucose molecules, and it'll release glucose molecules when you need glucose to make ATP. Exchange reactions, also called displacement reactions. Bonds are made and broken on both sides of the equation. What you're doing is you're just exchanging products and reactants. So A and B, molecule AB plus C will give AC plus B. Another example is molecule AB plus CD will give AD and CB. So you're just moving around, you're exchanging different sides of the equation to create a different product. And here's an example. Bonds are both made and broken in a displacement reaction, going from ATP plus glucose to ADP. You're just moving molecules around. So that's just a displacement or exchange reaction. Types of chemical reactions in living systems, these reactions are often referred to as a reduction-oxidation reaction. We simplify that and we say a redox reaction. And this is when atoms are reduced when they gain electrons and oxidized when they lose electrons. What that simply means, in this example, glucose is oxidized because it's losing electrons. It's losing electrons because it's being broken down. Remember, electrons make up bonds between atoms. So if glucose is oxidized, it's losing electrons, it's losing bonds, so it's just being broken down. And an oxygen molecule is reduced because oxygens in this equation are gaining electrons. They're forming more bonds. And this, we're gonna come back to this equation. You can work on memorizing it right now if you want. It won't be on this test, I don't think, unless we do cellular respiration, but this is just the equation for cellular metabolism in your cells, where you take glucose, you combine it with oxygen, the air you breathe, to get ATP at the end. So a redox reaction, in all body reactions, there's a reduction and an oxidation, and that just means some things gain electrons and some things lose electrons. If you're confused, all that means is that some things will break bonds, lose their electrons, because they'll lose the electrons when the bonds are broken, and they'll gain electrons when a new bond is formed with something else. That's all that a redox reaction is. Energy flow, chemical reactions can be exergonic or endergonic. So exergonic reactions just give off energy, and endergonic reactions use up energy. All chemical reactions are theoretically reversible. So theoretically, all reactions could go in both directions, meaning we could break down a product into its reactant parts if we had the right conditions and set up to do so. Most oftentimes they might be only in one direction, but all chemical reactions are theoretically reversible. Chemical equilibrium occurs if neither a forward or a reverse reaction is dominant. So that just means if A and B exist in your body as separate components in the same concentration as they do as one molecule. So that's what we call chemical equilibrium, if they both exist in really the same kind of concentration. Many biological reactions in your body are reversible, and we'll get to this especially when we talk about the pH levels in your blood and how carbon dioxide gets broken down into a component that controls pH levels. The rate of chemical reactions, so how fast or slow these products can be made from atoms or elements being bound together. Temperature can increase chemical reactions. So an increased temperature, if we throw more reactants in somewhere, that'll help the reaction go faster. And that just makes more sense. With more reactants, the faster the chemical reaction will occur. And the particle size, smaller particles usually increase the rate of the reaction. And that's because everything needs to bounce off of each other. So something that's smaller will be able to react a lot faster than a larger particle. A catalyst helps to increase a chemical reaction rate. And an enzyme is a biological catalyst in the body. And we'll learn a lot about enzymes in the body and specific ones. A catalyst will increase the rate of the reaction without being chemically changed or becoming part of the product. So that just means a catalyst kind of holds the hand of these reactants in a chemical equation. It won't be changed, it won't become part of the end product, but it'll just help go a little bit faster. And I think the next PowerPoint will kind of start with catalysts, but we will do that on Thursday.